right, here we go. Today we are going to talk about capacitors.
I don't see the problem.
Go. There it is. Sure, Lillian, you're required at the door. You want to hold that open? That'd be great. Okay. So we've actually described capacitors in a general form, in the form that basically it's two flat plates. This is the situation that has been causing a constant electric field between the two of them. AKA this right here. There is a flat plate, there is a flat plate, and I would say, hey, there's a bunch of positives over here, there's a bunch of negatives all over here, and that would cause a uniform electric field. Now, what you didn't know is the reason how that gets caused is that's usually connected to a battery. Now, a battery, as we said the other day, has a particular voltage across it, potential difference. And that potential difference is created how? How do you get, in general, a potential difference?
Two different charges.
Separate charge. Yeah, it's a little bit different from what you said. Make sure we got that. Separate charge. So you take a neutral object and separate its charge from one to the other. What do those negatives want to do? Well, they want to repel all the other negatives and attract to the positive side. Ultimately, that means that there is an electric field between them. So like if I take a set of neutrals right here, okay, and somehow separate them out, okay? So I move, let's say, the negatives over here. Now, all these negatives are repelling each other. All these positives are attracting the negatives, trying to pull at the other side. So there is now a potential difference between the two. So when a capacitor starts off, it does not have this. So let's actually, here we go. And I'm going to kind of draw this a little bit more three-dimensional-ish. So two flat plates. So what happens originally to these plates when connected to a battery? You're going to need to be a lot more specific. There's a lot of details going on here, guys. Let's make sure to cover all of them. So we got a battery. It's positive and negative. What's going to happen? Start with the left plate. What's going to happen? Correct. This is neutral, so there's an equal number of positives and negatives. And so this positive right here is going to pull negatives in that general direction, causing the plate to be positive. So I pull one, I pull two, I pull three, I pull four. And as I continue to pull more and more electrons off the plate, what happens to the ease with which electrons leave? It gets harder and harder to pull electrons off that plate. Why is it harder to pull electrons off that plate?
Because they're
positive right up here is doing what to the electrons? Pulling them back, right. And then vice versa over here. We've got a negative side of the battery, so what's it doing? Pushing excess electrons on up here, and for the same reasons we just stated, as I put more and more electrons up here, as I put more negative on this side, what happens to the ease with which we put more negatives on there? It should be harder and harder to do. So eventually what will happen is it will become too hard to put any more on and it will stop. When will that occur? When the potential difference between those two plates is identical to the potential difference of the battery. You can kind of think about it like, I kind of gave one analogy. I'm sticking with the hill of kids. All right, so imagine it kind of like this. You've got a hill, this represents the battery over here. Okay, and you take somebody and he starts pushing kids down a hill. All right, and this creates its own hill, right? Now, currently, can I push more kids onto this hill? Sure, absolutely, okay? So I push more kids onto this hill and the hill gets higher, right? When will I stop being able to push kids and actually get the kids to go onto this hill? Once the hills are of equal size, correct? Now this, as a heads up, okay, and this will come back a little bit later, is a hill of kids. Meaning, in terms of the dumb joke, but also like actually understanding it, the potential difference is created. I'm back up here by the charge that I just put on here. Yes? So ultimately, what is a capacitor for? A capacitor is another way to separate charge, aka another way to get a potential difference, aka another energy source. Capacitors are fantastic for spots in electronics where we need a burst of energy very quickly, but we don't need it continuously. Spots include starting up almost all electronics. I mentioned your TVs last time we talked about this. All computers are going to use this. Most of your cell phones, you'll notice that you cannot start them up very, very quickly. One of the reasons, of course, is the charging of capacitors that are within that. But we don't need to keep starting. It doesn't need that amount of energy to keep the thing going. It just needs it to start. Another spot that you could think of would be, well, a perfect example would be a defibrillator. A defibrillator is a capacitor, which we'll talk more about in depth in just a second, or like the flash on a camera, right? So if you want to charge your camera, you can just kind of charge a capacitor right over here, and then it needs to lose that burst of energy very quickly, and there we go. Yes?
Why do capacitors let energy flow more quickly than a battery?
Because of the process by which they release that particular energy. The battery uses a chemical reaction, which is not quite as fast. We'll talk more about that next chapter. Relative to basically, it's just this. I've got a metal positive, I've got a metal negative made entirely of a conductor. All you got to do to release all that energy is touch. And all the energy goes from one to the other. Ultimately, how this is usually set up is you've got some, let's say, device right here, probably being run by this battery, okay? So that electricity flows through this device continuously, and then it's also connected to the capacitor, and the capacitor probably has something of right here, connection here. So this negative will flow through into the device, and over here, the moment this little switch is just shut. We shut this, all the energy flows very quickly from one side to the other. All right, so, yeah, oh, it's on the wrong spot, that's why. Good night. It's all right. Okay, I was on the wrong side. So, how do we change? And then we talked about this capacitance. Capacitance is a measurement of how much charge you can store on a particular battery, on a particular voltage. Its equation is Q over delta V, or coulombs per volt. And as I mentioned the other day, that SI unit is just a farad. But as coulombs, you don't usually get a lot of charge on this. The standard capacitor is usually in microfarad. It's a very, very common capacitor. As a matter of fact, if you fully charged up a 1 farad capacitor, that would suck. If you touched both sides of that, that would be a lot of energy out extraordinarily quickly. So right here, it's just the main thing to get out of capacitance is just simply this. If I have a battery, which is this symbol right here, hooked up to a capacitor, I won't use that symbol, I'll just draw a battery. Okay. If I have a battery hooked up, if I have a 3 volt or a 1.5 volt battery hooked up to this setup of a capacitor, there's only, what does that mean? It means, keep for right now. It means my hill is only so high, so I can only store so many kids, right? What's going to happen if I hook up a bigger battery? Does that change the capacitance, the ratio? It doesn't change the ratio. It simply changes the number of kids on the other side. As a matter of fact, I did this poorly. I apologize, because that wouldn't change the. No, it would. Yeah, it would change the. So if I hooked up a bigger battery, aka a bigger hill, we get more height of the hill, and aka how do you get more height of the hill? more kids. So in that equation, right here, if I were to hook up a different delta V, that will not change C, that will change Q. Cool? All right, moving on. So the question then becomes, how do you in fact change C? Well, if we come back right over here, what are the ways that we could find to store more charge? Well, there we go. Let's go here. The first simple thing I could do is make the plates bigger. Why would making the plates bigger help?
Because there's more room, so there's less area for them to repel.
Right. If this little negative here that are stored here are over here instead, right, is it going to resist as much negative coming on? No. So I could simply store more negative. Another way to think about that is a certain capacitor could keep a certain amount of charge density. Well, if I increase the area, I have less charge density because it's the same amount of charge spread over more area, so I can put more and more and more on there. The next thing is this. I can change, let's get rid of this and I'll answer your question, the distance between the plates. Why should that affect things? Well, these are not arguably, well, sort of, in a vacuum, it's what are these positives going to do to the negatives coming on here? Attract. And what are these negatives going to do to the negatives on the plate trying to get repel? Meaning that if I get these closer together, those forces will have a bigger impact and therefore increase how much charge I can get on. Now, this is a particular sticking point because you want to say this. This is a capacitor. What I just said is you can store more charge the closer they are together. More charge should also indicate more energy, right? And yet, with this particular situation here, what gets us more energy? Closer together or further apart? So there's a big difference. The assumption here, and here's the major difference in this scenario versus that one. In that scenario, we are assuming the voltage is the same. We're getting to the maximum voltage, aka there is no discharge. There's no negatives jumping from one side to the other, which is challenging to do, which is why I'll bring up something in just a second. So point is, I could store more charge if I get to the max height, the max voltage in both cases. Does this get to the max voltage if I have them closer together? No, it discharges faster. The voltage is smaller. You heard me say at 1 centimeter it would be 10,000. At 4 centimeters it would be 40,000. Point is, the voltage is different in this case versus that over there. So the next question is, how can I keep, I'm skipping around on the slides because I don't like that they don't do this. How can I keep them from discharging? How can I get that distance as small as possible? And all the while that's the case, there's one other thing this thing does. I could have a capacitor hooked up to a battery, and then what I do is in between here, I put a non-conducting material that I will call, I'll give a name in just a second, let's put that orange. So I put a non-conducting material in here, and this is known as a dielectric. There are two major things that the dielectric does. One that we mentioned just a second ago. Because this is non-conducting material, it keeps the charges. It allows the distance to get as close as possible while not discharging the charge from one side to the other. Basically, we don't want to discharge this charge sooner than we want it to actually go. There is another thing that the dielectric does, though. If I have charges like this, as we've stated, there will be an electric field. Yes? What will a neutral object do if placed in an electric field? Polarize is the word I'm looking for. Yes, it will polarize. Meaning, if I take a negatively charged balloon and set it next to this non-conducting material, here it's sitting in an electric field, aka it's going to polarize. Now, why won't this charge go anywhere? Because it's not a conductor, it's an insulator, it's non-conducting. So we put the dielectric as an insulator in the middle. And what's it going to do? It's going to polarize, aka what are the negatives going to do? And it's going to leave over here, so these are going to be positive. Yes? Now, why don't these negatives just jump onto the positive and take off? Because it's an insulator. Right. So once again, a dielectric is just a non-conducting piece of material that we put in the middle so that, one, we can minimize D, so it won't discharge like over here, okay? And so that we can also, it'll do that at the same time. So let me give you an instance of a dielectric. Hopefully you can see a little bit easier. So right here we have, there actually is a dielectric in the middle of those two. What is it? Air. Or pretty darn close air to a vacuum. This is what all dielectrics are measured off of. This is actually the worst dielectric. Still pretty decent. But basically this is given, I'll give a value for just a second. But here's another example of the dielectric now. Is it taking longer to get through? Yeah, and I could do even more than that. I could, let's see here. Dielectric. Hold on, let's make sure it actually sparks. Okay, so what you're noticing me doing there is, does it spark nearly as quickly when it's in the middle? So what are these then allowed to do? What's that? They store even more charge at the exact same voltage. So does that in fact affect capacitance? If I can store more voltage at the same, yes. So how do we handle these three factors? The three factors, once again, were area, distance, and dielectric. Well, earlier I told you that capacitance is defined as Q over delta V. This is kind of the effect equation, and it's looking how capacitance affects those two. As we said before, if capacitance doesn't change, then this ratio doesn't change. AKA, this is way too big, but if I had a capacitor of 2, all it would mean is if I had a 10-volt battery, I could store 20. If I had a 20-volt battery, I could store 40. Ratio stays the same. This equation is how we actually change it. What should area do to the amount of charge I can store? So increase, right? So where should I put it in my equation? Top. Very good. What about distance? What effect will distance have? Increase, right? So as distance decreases, capacitance should increase. So where should I put it? On the bottom. This right here, epsilon naught, you've actually seen before. That is a constant that is in your, I'll write it up here in just a second, but that's a constant that's on your AP equation sheet. And then finally, this is how the book puts it, so I'm going to put it like this. So this right up here is the definition, it's the ratio. This is what could actually change it. Okay, meaning, if I design a capacitor, what do I want? I want two really large metal plates, the smallest distance between them, and I want to use a dielectric. And here's how you basically do a dielectric. Dielectric, the ratio is kappa. Okay, K, it looks like a K. Kappa. And kappa is the ratio of the new capacitance to the original capacitance. To give you an idea, this is just going to be a table of constants. Okay, the dielectric constant is what it's known as. Okay, the kappa for vacuum is 1, meaning this is the equation that's perfect for a vacuum. If you want to combine these two equations together, all it is that, hey, the new capacitance is kappa times the old one, aka kappa times epsilon naught times area over distance. So I gave them to you as separate equations. If you want, you can just do this right here. And if there is no dielectric, well, then you can just say that kappa is 1. What in that particular case? Is that
Okay, maybe I'm stupid or just I didn't hear something. Wait, what is the difference between C and C naught?
C naught would be the original without any dielectric whatsoever.
Oh, this is okay.
C is assuming there is a dielectric now in it. So yeah, kappa is the dielectric constant.
Oh, okay. I just didn't know what kappa was.
No worries. So we had this conversation already. There's another way to calculate it that I don't specifically love. It comes from this equation right here, if you'll remember, is Gauss's law. Okay, electric field is equal to charge density over epsilon naught. Also, the voltage between them is electric field times distance, and the charge is simply charge density times area, where charge density represents charge per area. So charge per area times area gives you charge. Yes, so they're combining these all together using the definition of capacitance. Q is equal to charge density times area, boom, over voltage, which is equal to ED, and E is equal to epsilon charge density over epsilon naught, and you'll notice that my charge densities cancel, giving the equation that we discussed on mathematically, that we discussed kind of conceptually just a second ago. So there is the electric field in the middle of a capacitor. Capacitors are used all over the place. One of the main spots they're used is pretty much on every single keyboard. The way a keyboard is set up is that you have a dielectric between them. You have two fixed plates. By tapping one down, you lower the distance between these two guys right here, ultimately changing the voltage, and that's how it measures most of the time which keystroke has happened. These are elements you probably want to have down. We'll talk a lot more about these next chapter. You can see me sometimes. Basically, quick elements for circuits are ways to kind of write a circuit very quickly. Again, we're going to write a lot more circuits next chapter. Well, we're going to write some of them in just a second. But a capacitor, well, that's just two flat lines. Kind of makes sense with what it is. A battery is one long line, one short line. If you had to guess, what's the difference between the short line and the long line? Backwards to that, but yes. But they're opposite charge. The long line is the positive line. So this right here would be, this shows you a picture of something on the left side and then how you would draw that circuit element over on the right. We have a 12-volt battery. We have a light bulb. A light bulb, actually, I'll tell you right now, a light bulb is really just a resistor. It's a resistor with a circle around it. So this is one symbol for a light bulb. The other symbol that you can use for a light bulb is just this, which is a resistor just with a circle around it. So. All right, so let's talk about capacitors in parallel. Actually, I'm going to come back to this real quick. I'm going to just show the slides real fast. I don't know why they do this out of order. I'll come back to that in just a second. Oh, they do energy too. Why do they do capacitance? Or why do they do? There it is. So here is a dielectric at the very end. Okay. This is, I showed you capacitance. They do it backwards with voltage. It works the same way. But here you go right there. The old equation for capacitance, the new equation for capacitance, and the dielectric constant is all of these guys right here. The most commonly used, because of its ease, for a dielectric constant is oil. Usually oil is what it is. So how do we make a capacitor? It's real simple. You get two flat sides. Does anybody know what a capacitor actually looks like? Let me go get one real quick. I know you've seen them before, whether or not you actually recognize them.
Are you okay?
I didn't do any of this series of parallels. No, now they're not, but I just didn't understand. I did most of them. No. Everything is because the thing about insulators is when you assume the two plates do the thing it but the charge of air is so spread out that you can't polarize them all. But you want polarization. Because if there's nothing to conduct, then the charge will just never come through, and that's bad.
Alright, this gigantic thing right here is 1200 microfarad or 1.2 millifarad right there. Okay, now you will notice they're almost always in cylindrical form. This is, well, just a second. Okay, this right here is 220 microfarad. That's a pretty large one as well. So if you've ever looked at a circuit board and seen kind of these like cylindrical things sticking out the top of them, that is a capacitor that you got. That might not be a capacitor actually. I thought I actually bought a 1 volt one. Maybe this is the big one I bought. Anyway, the reason why they work like that is essentially this is the easiest way to make them. You need to make a capacitor, as I've said, a bunch of space. So I need as much area as possible. Now, of course, the one way that I could do that is I could make it taller, but that's going to make the thing stick out. So the easiest way to get more area is just to make it longer and longer and longer. But obviously, I don't want to fill the entire space with this giant long thing. And what I want to also do is put an insulator right in the middle of there to be a dielectric. So they figure, well, let's just do this. Let's put an insulator in the middle and around the whole thing, and then what simple thing could I do for space? You guys ever eaten a Swiss roll?
I'm getting hypnotized.
Basically, it's take these and wrap them up into a cylinder. So that's why they always form a cylinder. Here, I took a picture a few years back. I took one apart. Let me see if I found that, where that's at real quick. Oh, come on.
Yeah, what happens to the plate?
So your two flat plates, you put them next to each other, right? You take the flat plates and imagine you have like two rugs or 2 blankets, and you simply Swiss roll them so they can get really close together, the smallest distance, and you would worry about that if they touched, but they're not going to touch because you have an insulator kind of surrounding both sides of everything. So I'll show you a better visual here. Where's my electricity? That's IPS. That's not home. The capacitor is the easiest way for them to screw up is that because they're confined in such a small space, if they have extra energy, where does extra energy go? Thermal, okay? And what would happen if you had a bunch of extra thermal energy in a confined space?
It would probably explode.
Now, they don't explode in quite the same way, but if you've ever seen basically a capacitor that is busted, there's probably like almost like an expanded spot on one of the sides because the gas has gone out. There's too much energy, and what do you do with all electronics when something breaks like that? Take it out, replace it, put the new capacitor in that spot, and go through it like that. All right, there we are. Electrical energy in class, capacitor, Porky Pig. That's all ending. Nope, that's not it. Capacitance problems. It might be here. Actually, I think it's right here. Yep, here it is. Okay, so I took this apart one year. Here is a capacitor. Rip it off. There is usually a conducting outer surface. The reason why is that if there is some type of thing getting in there, it should just connect and flow elsewhere. Here's the capacitor right here. If you unpackage, these aren't great pictures, I apologize, I should probably do it again with a better camera. But unpackage it, you'll see all the insulation right over there that has oil on it to be a good dielectric. And we have, I kind of broke one in part, but 2 flat plates sitting next to each other. In the middle of them, that's a capacitor. So how do I change a capacitor? Physically, you change its area, you change its distance, or you change the dielectric. But can you change the dielectric or the area, or the distance of this guy right here? No. So what do you have to do to get a different capacitance? You use a different capacitor. You plug in a different capacitor in that place. If you don't plug in a different capacitor, this is what I talked about at the very beginning, you put in a new battery, you don't get more capacitance, you simply get more charge, because capacitance is the ratio between the two. Questions, concerns? Cool, yes.
If each side of the capacitor has a different area.
They don't. They're the exact same area.
Okay, so it'd never be like that.
Well, you wouldn't make them like that. It would be redundant to have one side that was bigger than the other, just like this guy right here. So once again, how are capacitors used? They're used for, well, you tell me. How's a capacitor used? For instant
use
of?
electronics.
Not there yet.
For my TV. Turns on my TV.
Just store
Storing charge is not the purpose, though. The net charge on a capacitor is just 0. What's the purpose of a capacitor? To store burst of energy. To have a burst of energy as Q goes from one side to the other.
Just the lightning bolt in my.
Yes. So, like we said, a defibrillator is a capacitor. Well, if you've seen any medical drama, the first thing they do is they take 2 metal plates and they rub them together. There are 2 reasons for this. Any ideas what the 2 reasons are for rubbing the plates together? They are twofold.
They're making them different charges.
Try again. Number 1, first thing is to neutralize them. The second is actually to start to break up the electrons, try to move them around so that they are easier to move in that capacity. Then, in the medical drama, what does the person do?
Throw it on the person.
Holds them over here. No, they don't.
Oh.
They hold them over here. Why are they holding them so far from each other? So they don't actually conduct and discharge. And now they wait. What are they waiting for?
Charge.
They are waiting for charge, and then they will hear a beep come from the other thing. Okay, that tells them that it's probably at full charge, right? And then they say clear. Why are they saying clear? So make sure that everybody knows what. Don't touch the person I'm about to hit with all of the electricity. Then they place them right here and right here usually. Why? What are they actually doing? Placing them on either side of the heart so that the electricity passes through the heart. A huge amount of voltage would cause basically the heart to have a huge beat. Boom! Really hard. If you ever got hit by a defibrillator, one of the assuming that you're okay and survived afterwards, one of the things that you would notice is basically your chest would feel ridiculously sore. Why is that? Well, all muscles run on electricity, every single one. We did this whole thing the other day when we were talking about this. Your heart runs on electricity. It can't help it but run on electricity. So what they're doing is running a huge amount of electricity through the heart so that it, boom, beats. But do all of the other muscles that are in there know not to beat or boom? No. They push as hard as possible. When someone gets electrocuted, what is the physical stimulus that you would look at somebody and go, they're being electrocuted? They would do like this, right? Why? Well, because every single muscle group in your body comes in a pair. Your muscles do not expand, they only contract. If you want your arm to go this way, your bicep pulls in. If you want to go the other way, your tricep pulling your whole thing out. So if electricity was passing through both my bicep and tricep at the exact same time, they are ultimately in a tug of war with my upper hand. And what's that going to do? Well, my bicep is winning, my tricep is winning, my bicep is winning, my tricep is winning very, very quickly. So why are people shaking? Because muscles are in tug of war with one another, pulling against each other, and that's what causes that particular stimulus. All right, so they did capacitance. Let's go back to energy. Let's talk energy real fast. Okay, now the energy in a capacitor is slightly different than the energy just in a standard voltage. If I just told you that, hey, this area over here and this area over here have a voltage between them, how would you calculate the energy between those two locations? If I said, hey, there's a charge, X charge, I'm going to put this charge right here, this 10 microcoulombs, I'm going to put it in one, it's going to move to the other. What equation would you use to calculate the energy? Yeah, you just multiply them, right? You would get that energy is equal to Q times delta V. The problem is we can't use that here. And here's the reason why. Let's go back to my crappy analogy of the hill of kids. All right. So, I've got a battery here. Okay? I've created a hill of kids. Now, the battery's not important. We're just worrying about the hill of kids. When I discharge this, what I'm doing is I'm letting kids run down the hill. Yes? What kids are going down the hill?
The ones at the top.
The ones that are making up the hill,
Yeah.
right? So this height of the hill creates a particular voltage. Yes? What's going to happen after this kid? This kid's going to roll down the hill. And how much energy is going to use? Q delta V. But what happens to the height of the hill after that kid leaves? So what happens to the voltage? It's going to be smaller. So the first kid is actually going to get the most energy, then a little bit less, then a little bit less, then a little bit less. And the last kid on the very bottom of the hill puts up how much energy? So ultimately, here's the way to look at this. What happens to voltage as the charge goes down? As Q decreases, the voltage should also decrease. Yes, in a linear fashion. This is the max voltage right over here. What's that max voltage of the capacitor going to be? Whatever the battery was, assuming it's at max charge. Yes? So let's say a 12-volt battery. 12-volt battery. What is the minimum voltage going to be when there's practically no kids on the hill? Since this is linear, what we can do is we can use a average. Right? The voltage is not constant, but the average is. How do you get the average? We would take delta V max, right, plus the minimum divided by 2. Everybody cool with this? So if I wanted to know how much energy I would get out of a capacitor, that would be Q, the total amount of charge stored on the hill, times delta V over 2. Or the energy stored in a capacitor is 1/2 Q delta V. Now that is pretty darn close to this guy, but what I found when going through electricity is that students struggle with when to use what versus the other one. So, when do I use that one? The voltage isn't changing for any particular reason. Why do I have to use this one with a capacitor?
Because the voltage is changing.
Because the voltage is changing as the charge rolls down the hill. Does that make sense? Now, what is very common in electricity is to make new equations. Now, I will tell you right now, the two equations that I'm going to discuss are this guy and that guy. And I'm going to make the new equations. You're welcome to use the new equations, but I think it's very important to understand how they work. Meaning, if I hooked up a new battery, okay? If I doubled the battery, and I look at this equation, I said, how should that affect energy? Somebody not paying attention very quickly would go, oh, if you doubled the battery, it should go up by 2. Except that is not the case here. The actual answer is 4. Why? Why should the energy go up by 4 if I double the size of the battery? What's that? Because charge will also go up because of the battery, meaning voltage at the same capacitance doubling should mean I have twice Q. So if I have twice Q and twice the voltage, I should go up by 4. Does that make sense? Okay. What if I, instead of hooking up a new battery, okay, let's just discuss this in your group real quick. I keep the same battery, I double the capacitor. Discuss quickly in your group what effect would that have on the energy. If I double the size of the capacitor, I was at 10 microfarad, now I'm at 20 microfarad. What effect should that have on energy? So what effect will that have on energy? it should double, right? Because doubling the capacitor, will that have any effect on voltage? Nope, not so whatsoever. Voltage is controlled by the battery, but it would double the Q, and therefore it would double energy. Does that make sense? So ultimately, I like when people use these two equations to come up with their line of logic. However, the next couple of equations will also help you just using a little bit of math. I'm going to take that guy and I'm going to solve it for Q. So these are my starting equations, this guy and this guy. These are really the important ones. But I could also solve this for Q. What would this be with Q? C delta V, okay? Which is why if I doubled the voltage, I'd get twice as much. If I doubled the capacitance, I get twice as much. Now I could take that equation and substitute it in over here, and I get delta U equals 1/2 times C delta V squared. The nice thing about what I just showed you is now you can see from this equation, my first question, hey, I double voltage, what effect should that have on energy? You can see right here that it in fact went up by 4. There's another equation, though, that you could use as well. And it would come from this guy and solving it for delta V. What is this guy if we solve for delta V? Q over C, right? So I could take this guy right here and plug it in there, and I would get another new equation. Now, how do I know which of these equations to use? What it really comes down to is when you're given a problem like this, you will be told something to this effect. What I told you originally is I said, hey, you hook up a new battery. What you should have heard there is I just doubled the battery, but the capacitance stayed the same. So I would look at this guy because I know that guy doubled and that guy stayed exactly the same. I could say this. I could say what should happen to energy if the charge cuts in 1/3 and the voltage goes up by 2. Well, then you would look at this guy. Charge cut into 1/3, voltage went up by 2, so the energy should be 2/3 of what it previously was. Or finally, what if I double the capacitance, but charge also doubled? Okay? I'll explain why that's a weird question in a second, but you would go right here and you would go, well, I doubled charge, so that would make it go up by 4. Doubling capacitance would actually make it go, that should be going only up by 2. Does that make sense? Now, it's weird for me to say that you keep charge the same or you double charge, because can you actually control charge? No. The only thing you can control is what the capacitor is and what the battery is. So what would have to take place in order that you double the capacitance and double the amount of charge? Well, doubling the capacitance while doubling the amount of charge should be the same as this right here. Doubling charge, doubling capacitance. What would have had to happen with this guy? Nothing. It would have stayed exactly the same, in which case you would have been dealing with this situation right here. The voltage stays the same, the capacitance goes up by 2, so it also should show that it goes up by 2 in that particular case. So, point being, if I were you, I would get very good at understanding all of these in terms of just these two equations first. That's what I would do. But if you feel like you're comfortable with it, these can provide a little bit of ease and quickness in doing these problems. All right. Trying to figure out finished capacitors real quick here, because now we got the tricky part. What if we put capacitors in parallel versus what if we put them in series? The word parallel means that you are, it's not actually parallel like it is in math. Okay? Now, we do tend to draw it that way just to keep things simple, but ultimately parallel means they have two different paths that you can hook up. And what I would suggest you look at when looking at this right here is simply what other effect does that have on the original equation of this guy right here? What is putting them in parallel really kind of affecting? Area. So if I have more area, what should that do with the amount of charge? I should have more charge. Right, because ultimately I have more area. So all the rules I'm about to show you kind of go hand in hand with that. Okay? Now, capacitance is the ratio from charge to voltage. Charge to voltage. What is the voltage on both of these? Well, imagine that you've got this, and this is where analogies can be super helpful. This is two separate paths. So this is like the same battery charging two separate hills of kids. Okay, I put some kids here, I put some Q here, I put some Q up there. What should be true of the heights of both of these hills? They should be the exact same height. Meaning, the voltage on this battery should be the voltage across here and the voltage across here. Now that's confusing because I'll say, hey, this is a 12-volt battery. And you go, well, how can this one be 12 volts and this one be 12 volts? Isn't that 24? And the answer is no, because they are two entirely separate paths. Can a kid be stored on one hill and the other hill? No. So if a kid goes from the top of this hill to the bottom of this hill, are they going to get the exact same amount of energy as the other hill? So in my picture, it's back to my dumb picture of the kids. Where'd it go? Oh, it was at the top right there. It's essentially, again, you have one battery charging one hill, and you have the same battery charging a second hill over here. We're saying both of these hill heights are the exact same amount. But will that change the amount of kids stored on this hill? No. It's exactly the same ratio. So in parallel, this guy is the exact same as if it were by itself. But I've got a whole other one that's also being charged at the same time. So does the individual Q change? No. Does the total amount of charge change? Yes. And here's the rules real quick, and then I'll answer your question. I know I'm not answering questions very good today. I want to finish this off first. So charge total, the total charge is the charge of 1 on the first capacitor plus the charge on the second capacitor. This equation simply comes from the definition of capacitance. Capacitance is Q over delta V, so Q is equal to C delta V. Notice that the voltage on this one and the voltage on that one don't have subscripts because they are the same amount, because it's the battery. So if I take these two equations, or all three of these equations, and combine them together, let's actually do this math separately here. Here's what they just said. Come on. Why am I struggling so hard? The charge total is equal to the charge on 1 plus the charge on 2. Yes?
Yep.
And the charge of 1 is equal to the capacitance of 1 times the voltage of the battery. The charge on 2 is equal to... Come on, dummy. Why are you struggling so hard here? Because I'm trying to go quick. Is equal to the capacitance of 2 times the voltage. So the capacitance total, the charge total is equal to the capacitance total times voltage. And what is true of all of those voltages? They are the same. So the capacitance total is simply equal to the capacitance of 1 plus the capacitance of 2, if they are in parallel. What this allows us to do is it allows us to take a circuit such as the one written on the left here, take these two and combine them together. Meaning I can go, hey, there's 10 coulombs on this. There's 10 farad here. There's 20 farad here. Let's pretend like it's a 30 farad capacitor. How are we doing? Ish. Okay, cool. Moving on.
Wait, can I ask my question?
You go ahead.
Okay, so see how the things are like set up, so like one's like behind the other? The negatives would like go in there, like once the negatives were pushed into like one side of like the capacitor, like one of them, wouldn't they push them away and keep the other electrons from flowing into the other capacitor? Am I just
No, when you're dealing with wires, which is what everything that is not a capacitor is here, we are assuming there's basically perfect flow through them. They should not. It's not entirely true, but for the most part, they don't limit how much electricity goes through either side. I see what you're saying. Like as the negatives leave here, and there's a negative here, wouldn't that keep these negatives from going? Think of a wire. Think of a wire as kind of like a lane of traffic. Okay. And if I say it has no resistance, that's like saying, imagine a lane of traffic. So like you're thinking kind of like if there's like 3 lanes of traffic, right? Having traffic in that all 3 lanes would keep charges from getting on the interstate and slow stuff down. When I said there's no resistance, it's like having a 40-lane highway.
Okay.
Okay?
Gotcha.
So is there negative in there that should repel? Sort of, but there's plenty of room for everything to flow in a wire.
Okay.
It's a good question. It's a good question. All right, next. What if they're in series? Okay, so parallel means there's 2 separate paths with 1 on each. Series means there's only 1 path. And if you follow my analogy from before, if them being in parallel is like charging 2 separate hills, them being in series is like taking the hills and stacking them on top of each other. Okay, so if I were to take these hills from my picture and stack them on top of each other, here we are back here, instead of making a whole separate one, I still only have a max height that I can get to. Yes? So I would have 1 hill plus the second hill. Will either capacitor get the full amount of voltage of the battery? No, it's going to be split. So here we go. The voltage is equal to Q over Q equivalent. Okay? And if we look at the voltages, now instead of the charge being split between the two, the voltages should be split between the two. And, this is kind of hard to see, but the charge total on this guy should be equal to the charge total on that guy. By charge total, I mean the magnitude of one or the other of them. Okay? Why is that? Well, this positive is going to take negatives off of here, right? This is going to put negatives over here. And notice that this center guy right here is not actually connected to anything. So why should they have different charges? Well, what is this positive going to do to negatives in this wire? Pull them this way, making there be a negative charge due to polarization. And if this negative charge just went over here, guess what charge that's going to be? Equal, but the opposite of whatever we just pulled over just a second ago. The hardest piece to get out of series is recognizing that the charge on capacitor 1 is equal to charge on capacitor 2. If they are in series, so if you go back to parallel, here's what we said with all the relationships. Let's go here. I like this. Okay, here's what we said with all the relationships. We said the voltage of 1 is equal to the voltage of 2 is equal to the voltage total, where the total is the voltage coming from the battery. Okay? Then we said charge total, which would be the total charge charged by the battery, is equal to charge 1 plus charge 2. So all the charge stored here plus all the charge stored there. We got kids being stored on 2 separate hills. The final equation that's very necessary to get is simply this. It is that the capacitance equivalent is simply equal to the capacitors, and I'm going to put ... because if there are more capacitors, it works the same way as long as they're all in series. If you go to series rather, it's this. The voltage total provided by the battery is equal to the voltage of 1 plus the voltage of 2. Or in other words, what that says is if I stack my hills on top of each other, both of the 2 of these combined will equal the total original hill. So can either one of these ever be bigger than this guy? No, absolutely not. This equation can sort of give you the idea that it's these that cause that. It's sort of the opposite, right? This is just kind of the limitation. And then I said a second ago, charge total, which is the total charge put out by the battery, is equal to the charge on plate 1 is equal to the charge on plate 2. Now, the equation for capacitance is a ratio, meaning any ratio basically says, if I know one of them, I automatically know the other. Yes? If I have capacitance and I know voltage, I can get charge, or if I know charge, I can get capacitance. So what I can do using this equation and this equation right here, well, actually, let me rearrange this. This equation rearranged is that the voltage is charge divided by capacitance. Yes? So what they're going to do now on the next slide is use those relationships along with that and start plugging them in. This will be Q over C total. I see it's equivalent. I'll talk about that in a second. This is V1 is Q over C1, and V2 is Q over C2. Why don't any of the Q's have subscripts? Because they're all the same. So when I plug them in, I get this. Delta V total is equal to V1 plus V2. So this will be Q over C total, Q over C1 plus Q over C2. And what are all the Q's going to do? Oops. Dummy. Would you stop being wrong? Now, I will leave it to your mathematical mind to recognize that no, you can't simplify that any further. Can't I just take the inverse and isn't it exactly the same as the others? Oh, no. No, it definitely isn't. Another way to write this is simply this. The inverse of those added together. I'll show you a very simple example to prove that they are not the same. If I said, let's do something very simple here. Come on. Let's say I have a capacitance of 3 and a capacitance of 4. This would be 1 over 3. It's 1 over 4. If I take the inverse, somebody not paying very close attention would go, oh, it's isn't that just 7? Nope, because if you want to add these together, what should it be? First thing you're going to do is common denominator, which is going to be
4 twelfths and 3 twelfths.
So you're going to get 7 twelfths, and then you're going to invert it. So are you going to get 7? No, you're definitely not going to get 7 when you get this in this case. Now, I will show you a good trick to know about these two rules. The two rules being this guy that we had a second ago, this guy right here. This is for what? Parallel or series? Series. And the one for parallel looks like this. Oh, just wait, it gets worse. So I shouldn't keep saying that. That makes it sound like. But the good rule, and this one's the easy one to spot. Okay, equivalent capacitors when they're in parallel are bigger than the biggest. Okay, bigger than the biggest. Now this one probably pretty easy to see. So in other words, if I had 7 and I had 2, right, the biggest here is 7. Of course, the total is going to be bigger than 7, right? You can easily see that. But along those same lines, if you look at this, the actual opposite is true. The total will always be smaller than the smallest. So what was the smallest in my example I gave just a second ago? 3. 3 was the smallest capacitor. Because the capacitor is not 1/4, the capacitor is 4. So the smallest was 3. Is 12/7 smaller than 3? Yes, it will always be that way. Yes?
So what is like an example of like why you would use like a series one rather than like a parallel, or a parallel rather than a easier.
Fair enough. So this is easier for me to do with resistors, which I hate that they kind of do it in this particular order. It makes sense because they're learning capacitance right now. Maybe I should put this in the future in the next chapter. I don't know. Anyway, ultimately what you're trying to do is you recognize that it all comes down to what was the purpose of a capacitor? Store energy. So the whole purpose comes down to this guy right here that we talked about a minute ago, right? You want to store a certain amount of energy, right? So you need to be able to control Q and delta V. I can get more energy out of either of them. I can get more energy out of taking more kids down a tiny hill, okay? Or I can get more energy out of a gigantic hill and fewer kids, okay? Or I could quadruple it if I get more of both, right? So changing what series and parallel are basically allow you other opportunities to change Q and delta V while changing some other things. I think it'll be a little more obvious when we really start to get into circuits the next couple of chapters, and you can start to see like, oh, I can manipulate delta V and something else that we'll get to a little bit later on. So ultimately what it's going to come down to is a problem that looks like this. If you can do this next problem, you're all golden. Let's cover it real quick. Okay, I'll give you a battery. This will be a circuit. Let's go just 10 volts just to make our lives easier. Okay, and up here I will put a capacitor that is 4 farad. Now obviously it wouldn't be that small, but I'll just keep it simple for the sake of right now. Followed by 2 more capacitors, one running at 2 and one running at 3. A common question that would be asked in this particular case, what is the charge and voltage on every single capacitor here? Now, you might notice that I was trading back and forth between these, capacitance total and capacitance equivalent, EQ. EQ is what it actually is, and basically as you look at this, okay, are all 3 of these in series or parallel? The answer is no. All 3 of these are not in series or parallel. Parallel is 2 different paths with 1 object down each. Now, these 2 are in parallel with each other. But is this an entirely separate path for this guy? It's not a, well, yeah, I guess you could make that sentence yes or no, depending on how you want to look at it. Meaning, let me show you this. These are all in parallel together. They all start at the same spot. They all end at the exact same spot. They each have their own individual separate path, right? Is this a separate path compared to those 2 right there? No. So this is not in parallel with those 2. Series looks like this. This is all 3 of them being in series. 1 path, they're all on the same line. Is this 1 path and all 3 are on the same line? No. So here's what you have to do. You have to recognize that these 2 are in parallel, and actually this guy is in series with the combination they're in. So here's what you do. You redraw the circuit. Like this. Now, how did I get from 3 to 2? Well, I can find the equivalent of this by using this rule right here. What is the equivalent of these 2? 5. Now that I've done that, are these 2 now in series or parallel with each other? They're in series. So how would I combine them together?
You just do the equation.
Yep. So you get what? 9/20ths. So the answer is 29ths. I thought the numbers were going to end up easier and nicer than that, but that's okay. So this right here, this is an equivalent resistor. Why? Because that 5 is equivalent to the combination of these 2. Why? Because in parallel there's more area, And since there's more area, we should get more charge, which is exactly putting a 5 down here would have more charge, right? I realize now that I didn't actually talk about series in that same way. What is changing if you add series? Area is not changing anymore. What's changing? Distance. What's happening with distance? It's getting bigger, so what should happen to the amount of charge stored? It should decrease in that particular case, yeah. So, I said at the beginning of that problem that what you're trying to do is you're trying to get the charge and the voltage on every single capacitor. So here's what I'm going to do. I figured out that the total capacitance is 20 farad. So what I can do now is this. Do I know the total voltage? Yeah, what is it? 10. So I can take this equation. Since I know the total capacitance and the total voltage, I can get that the total charge being stored is 20. I'm going to go back and reverse my original problem so that I can make our numbers nicer. I'm going to say it was a 9-volt battery. So it's 20 coulombs. Obviously, these numbers are ridiculous for the purposes of keeping our numbers simple, but let's work our way backwards. Now, here's what you do. When you draw these, always redraw the circuit. Meaning, if you do an equivalent capacitor, redraw the circuit again, and watch what I'm now going to do. I'm going to use the rules that I said a second ago. Basically, what we just did is we said, hey, this is 9 volts. This total capacitor is 29 farad. How much charge is stored there? And we got that the charge being stored there is 20 coulombs. What is the same for both of these capacitors? Charge or voltage? Charge. And do you know what that charge is? Yep. You know it's 20 coulombs. Okay? You know that on this guy right here, there's 20 coulombs, and this guy, there's 20 coulombs. Why? Because all charge in series is the same on every capacitor. We talked about that rule earlier. And if you know charge and you know capacitance, can you figure out what voltage is? Yes. The voltage of this guy right here should be charge 20 divided by the capacitance 4 farad. So how many volts should be on there? 5. That would be the voltage across this guy. And the second one should also, I screwed this symbols up, my apologies. That should not have been farad on top, that should have been coulombs. 20 coulombs divided by 5 farad, and so that should be 4 volts. And why does that make perfect sense that this should have 4 volts on it and that should have 5 volts on it? Well, because together they should probably add up to the original hill of 9 volts. Yes? Now I said at the beginning that we were going to try to find the voltage and the charge on every capacitor. Do we know the charge on this guy? Yes. Do we know the voltage? Yes. So if I wanted to figure out how much energy that was storing, that would be 20 coulombs times 4 volts. That stores 40 joules. This capacitor here stores 40 joules. Now let's take it one step back further. What is the same? I know that this total has 20 coulombs and 5 volts. What is the same between this guy and this guy? The amount of volts is the same. So this should have 5 volts, and this should have 5 volts. Which means now you can use that equation, C equals Q over delta V, to get how much Q, simply because Q is equal to C times delta V. So how much charge is stored on this guy? 15. How much charge is stored on that guy? 10. Did I do that right? I did something wrong. Oh, I did them backwards of voltages. That's the issue. I said this was 4 volts and this was 5. It was the opposite. My apologies. So this is actually 4 volts, and this is 4 volts. So what should the total charge be stored here? 12 and 8, which makes sense because what should it add up to? 20. Practice these tonight. I would imagine this is where a bulk of your questions are coming tomorrow. Okay, so I'll give you another sample one to work on in the last 5 minutes. Okay, it's kind of be the opposite of what I just did. Let's go. Let's go. This is 2 farad. That's 1 farad. Actually, no, let's go different. Go 4 and 2. Darn it. So doing it so challenging. What would make it easier? Yeah, we'll do 4 and 2 and 3.25. Yeah. It doesn't look like it in the meantime, you know. No, I'm trying to math quickly here. Sorry, I should have got these.
It's in between the 4 and the 2.
What's that?
It's in between the 4 and the 2, right? It's not lining up with the 4. I don't know. I just.
The line. Okay, let me be clear. The parallel again. Is not actually parallel. I could draw this exact same circuit like this. It has nothing to do with the straightness of the lines or where they are. I could also draw this 2 over here, and it does not change a thing. Okay, so the spacing does not matter whether it's between or whatever. It matters what path it's specifically on. All right.
How many do we need to figure out?
We'll talk about this later.